All right. Ever stop and think about what's actually keeping your feet planted on the ground? Or how the moon stays up in the sky? Or even crazier, how a massive hunk of steel, a ship, can just float? Well, today we're diving into two fundamental, invisible forces that run our world: gravity and buoyancy. Let's do this. So, here's the big question that really got the ball rolling. You see an apple fall from a tree, right? Straight down, no question about it. But here's the thing. The moon is also falling. It's constantly being pulled by Earth's gravity. So why doesn't it crash right into us? This wasn't some simple trivia question. This was a puzzle that had some of the smartest people in history scratching their heads for centuries. And then along comes this guy, Isaac Newton. The story goes, and it's a great story, that he was just sitting there, saw an apple fall, and boom, a massive light bulb went off. He started to wonder, what if? What if the force pulling that apple to the ground is the exact same force that's holding the moon in its path? It was a wild, revolutionary idea. And you see, this wasn't just about figuring out apples and moons. Newton was thinking bigger, way bigger. He realized he might be onto something, a universal principle, a rule that applies to everything, everywhere in the cosmos. And this is what he came up with: the universal law of gravitation. Now, that sounds super formal, but the idea is actually mind-blowing. It basically says that every single thing with mass in the universe is pulling on every other thing with mass. You, me, the chair you're sitting in, this planet, the sun, everything is connected by this invisible force. It's not just for planets. It is truly universal. And the rules for how this force works are surprisingly straightforward. First, the more stuff or mass something has, the stronger its gravitational pull. A planet pulls way harder than an apple, obviously. But here's the really cool part: distance. As you get farther away, the pull gets weaker. But it doesn't just get a little weaker, it gets a lot weaker really fast. It follows something called the inverse square law. So if you double the distance between two things, the force of gravity between them drops to just 1/4 of what it was. It fades away super quickly. Okay, so let's get back to our moon puzzle. Why doesn't it fall down? Think about swinging a rock on a string over your head. That string is constantly pulling the rock toward your hand, right? But the rock is also moving sideways, so it just keeps circling. Earth's gravity is that invisible string for the moon. It's yanking the moon towards us always, but the moon has so much sideways momentum that it's constantly, well, missing us. It's in a perpetual state of falling toward the Earth, but moving sideways just fast enough to never hit it. And that, my friends, is what an orbit is. Okay, so we've got the orbit thing down. Now let's bring that huge cosmic idea right back home, to Earth, and talk about what happens when things don't miss and just fall straight down. Right, so when you drop an object, and we just ignore air for a second, we say it's in free fall. And it doesn't just fall at one speed, it speeds up, it accelerates. And it does so at a very specific, constant rate, about 9.8 meters per second, faster every single second. And we give this special rate a name, we just call it g. And this leads to a conclusion that still feels kind of wrong, even though we know it's right. In a vacuum, without any air getting in the way, a bowling ball and a tiny feather would hit the ground at the exact same time. The legend goes that Galileo Galilei actually showed this off by dropping things from the top of the Leaning Tower of Pisa. The big takeaway here is that gravity pulls everything with the same acceleration, no matter how much it weighs. But hang on a second. If a heavy thing and a light thing fall at the same rate, then what's the difference? Why does one feel heavier? Well, that brings us to a super important distinction: the difference between mass and weight. And this is the perfect way to look at it. Mass is just the amount of stuff an object is made of. Your mass is the same here on Earth, on the moon, or floating out in deep space. It never changes. Weight, on the other hand, that's the force of gravity pulling on all that stuff. And because it's a force that depends on gravity, your weight can totally change depending on where you are. Take the moon, for example. If you went there, your mass, all the stuff that makes up you, would be exactly the same. But you would weigh only about 1/6 of what you do here on Earth. Why? Simple. The moon has way less mass than Earth, so its gravitational pull, its g, is much, much weaker. Okay, I think we have a pretty good grip on gravity, this constant downward force. But that just opens up a whole new can of worms, a new puzzle. Let's switch things up and talk about water. Yeah, think about this for a second. If gravity is always pulling everything down, then why does a giant 1,000-ton steel ship float, but a tiny little steel nail sinks like a rock? I mean, they're both made of steel, which is way denser than water. Gravity is pulling down on both. What gives? Something else has to be going on. You can actually feel this something else with a really simple experiment. Imagine you have a stone and a scale. First, you weigh the stone in the air. You get a number. Got it? Okay. Now, keep it on the scale, but lower the stone into a bucket of water. Look at the scale now. The number's lower, right? The stone didn't magically lose any of its stuff. It just seems lighter. That lost weight is the result of an upward push from the water, and that push is called buoyancy. This is exactly what the ancient Greek genius Archimedes figured out. He put it into a principle. The upward push, or buoyant force, on an object in a fluid is exactly equal to the weight of the fluid that the object shoves out of the way. You know, the water it displaces. This was his famous eureka moment in the bathtub. So that's the secret weapon, Archimedes' principle. Now we have everything we need to finally crack the case of the floating ship and the sinking nail. When you get right down to it, it's all about density. It's a fight between two forces, gravity pulling down, buoyancy pushing up. And the winner of that fight is decided by an object's overall density. Basically, how much stuff is crammed into how much space. And here it is, the final piece of the puzzle. A nail is a solid chunk of steel. It's super dense. It sinks into the water and only pushes a tiny bit of water out of the way. So the downward pull of gravity is way, way stronger than the tiny upward push of buoyancy. It sinks. Simple. But a ship is a different beast altogether. It's mostly a huge hollow steel bowl. Because of its shape, it pushes a massive amount of water out of the way. It sinks into the water just enough until the upward buoyant force from all that displaced water is perfectly equal to the ship's entire weight. The forces balance out, and voila, it floats. So let's just take a step back and think about what we've covered. Gravity, it's the ultimate cosmic glue. It's what keeps us from floating off into space. It's what choreographs the beautiful dance of the planets and moons, and it even tugs on our oceans to create the tides. It's a universal force that dictates so much of our reality. And then you have buoyancy, which is just as important for us here on Earth. Understanding it is how we build ships to cross oceans and submarines to explore the deepest trenches. It's even the reason hot air balloons can fly. They're just floating on the massive ocean of air that is our atmosphere. So, we've gone from a simple falling apple to a massive floating ship, uncovering the hidden rules of two of the most powerful forces in the universe. We've seen how Newton's gravity governs the entire cosmos, while Archimedes' buoyancy lets us master our own world's oceans and skies. It really makes you wonder, doesn't it? What's the next great invisible force that we'll learn to understand and harness?